Hi, my name is Raymond Duenas. I'm a PhD research student here at UC San Diego, working to improve AI performance on edge devices. Systems like smart cameras, robots, and embedded processors where compute is limited, but responsiveness matters. Edge devices are expensive, not just in cost, but in carbon and silicon. Yet, when we run inference, we're often wasting the hardware we paid for. In this example, the GPU is fully utilized while the CPU is sitting idle. So that led to the question, is it possible, and how close can we get to 100% utilization of CPU and GPU? To start answering that, we tested 128 different configurations of a model split across the CPU and GPU. Each point here represents a different layer to processor mapping. As you can see, more GPU layers generally improves performance, but across all cases where the CPU was available, the best performing configuration was always the one where the fully connected layer ran on the CPU, freeing the GPU for earlier layers and allowing us to run parts of the model in parallel. So, did we succeed? Yes. This side-by-side comparison shows the transformation. On top, the CPU is nearly idle with the GPU carrying everything, as we saw before. But now, on the bottom, after splitting, both processors are active and working together. By restructuring inference, we're able to approach full chip utilization, and that led to gains in throughput performance. To test how general this method is, we implemented it across 3 different neural network architectures: MobileNet V2, EfficientNet B2, and VITS Tiny, all running on the NVIDIA Jetson HGX Orin, which included 12 ARM CPU cores, 2,048 Ampere GPU cores, and 32 gigabytes of shared LPDDR5 memory, ideal for evaluating unified memory behavior. Our goal? Split layers intelligently across CPU and GPU and see if this approach improves throughput across all 3 models. Here's how it works. Using Resident 50 as an example, at the top, you see the full architecture. Beneath it, we simplify it to make splitting more intuitive. In the traditional implementation, the entire model runs sequentially on the GPU. But in our proposed version, which we call unified splitting, the GPU handles everything up to the final pooling layer, and the fully connected layer is processed in parallel on the CPU. This gives us our pipeline. This is what traditional GPU-only inference looks like across 3 batches. Each batch has to wait for the one before it to finish, so even if one part of the chip is idle, the next input can't move forward. This is inherently inefficient. Now, here's the same timeline with our method. While the GPU is working on the convolutional layers of batch 2, the CPU is already finishing the fully connected layers of batch 1. This overlap creates a pipeline, a parallel pipeline, increasing throughput without sacrificing accuracy. When we zoom out to look at more batches, the benefit becomes even clearer. The top shows traditional GPU-only inference. The bottom shows our split method. You can see how much more efficient we move data with CPU and GPU both engaged every step of the way. To close out, here are the throughput results from all 3 models. We observed consistent gains across the board. What this tells us is that unified splitting generalizes. It's not just a one model trick. It works across architectures and offers real performance gains using the hardware already on board. And if you'd like to dive deeper into the methodologies, see the source code, or follow along with our research, scan the QR codes below here to visit my personal website or access the project repo on GitHub. Thanks again. I'm Raymond Duenas. I'm excited to keep pushing forward towards smarter, more efficient AI on edge devices. Finally, I'd like to give a special thank you to my advisors, Pat Panuto and Ryan Kastner, for creating this research opportunity and then allowing me to dive deeper through this last quarter, and Alexander Redding, who when I first started out on this project, having no idea what I was doing, was able to give me advice, direction, and insight in order to start out on the right foot. And lastly, NVIDIA for previously donating this to our lab and allowing me to have the opportunity to have advice to explore this research.